Okay, let's start. So I was going to talk about completing the square, which were the last two problems, but it looks like you guys figured that out, how to complete the square. So maybe I'll just talk about this one instead, number 9. So this is causing more trouble. We've got, so let's sketch those points. All right, I was going to sketch these 2 points, but that doesn't look fun because of where they are. What octant are those points in? What octants?
1, 6.
I have 6. I have 7. 7. It's octant 7 because it would be 1, back here is 2, back here is 3, up here is 4, and then down below 5, 6, 7 would be the one where all 3 coordinates are negative. Does that make sense? Like kitty corner from octant, the first octant, where they're all positive. Okay, so let's not draw those. That doesn't look fun. But the concept does, you can do this conceptually without a picture. So how are we gonna? What do we need to find the equation of a sphere? Center and radius, right? So our equation is x minus a squared. So how are we going to get the center? If these are actually points on the sphere directly across from each other. That's what they're saying. These are points in the sphere directly across from each other. So the segment joining those two contains the center, right? Right in the middle. So what would that point be? So the center would be half the distance, right? Or so halfway between each one. So -4, -8, -7. So you see that? And if you couldn't eyeball it, what would you do to get those coordinates? Yeah, it's like average, right? Halfway between would be like the average. You'd add them and divide by 2. And then radius? How am I going to get the radius now? Nick knows. So I've got the center, and I've got a point on the sphere. So you think about the vector, right? A vector from the center to a point on the sphere, and then you would need what about that vector? The magnitude of a vector. Say this is point P. So you need the magnitude of CP. Right? So a vector from the center to a point, the magnitude of that would then be the radius of the sphere. So I think you can take it from there. You got the center and the radius. Okay, let's just do the completing the square once for those, since I didn't demonstrate it, those who haven't done it yet. So the standard form has these completed squares, x minus a squared, y minus b squared, z minus c squared. So you'll see you could have it in this form, which is a sphere, but it doesn't look like it because it's not completed. So we've got x squared and 14 minus x. We need to complete the square to get a perfect square, x minus the a squared. Same with the y squared minus 16 and z squared minus 16. So how do you complete the square? If you have a coefficient 1 on the quadratic term, then you take half of the linear coefficient and square it. Half of the linear coefficient squared and add that on, and that completes the square. So it'd be x squared minus 14x. Half of -14 is? -7 squared is? 49. Similarly, you'd have y squared minus 16y plus half of 16 is 8, squared is 64. Does that make sense, what I'm doing here? But then, so then you do the same thing for z, but then over here you got -96. So to keep the equation, keep the balance of the equation, I added 49. So I got to have 49. And I added, what, 64? So I got to add 64. And then whatever I'm going to add here, It's like another 64. And then you can take it from there. So now you've got what? Perfect square trinomials. For instance, this one is what? X minus 7 squared. So I'll let you finish that. And then on the last question, you're matching the visuals to the equations, and you may have to do this a little bit also. Any other questions on the web work? So that's due today at 5. I'll post the next one, which will be due Wednesday at 5. I will not see you Monday. Yeah?
When I was in the tutoring center for problem 9, what's the relation between a vector and the distance formula? They were explaining to me to find the radius to just use the distance formula by doing x3 minus x1. So it's the same, that's the relation. A vector is magnitude 37 about the distance formula.
Gee whiz. What is vector PQ or QP? What is vector QP? No. Tell me your name again. I'm sorry, I forgot.
No, Ronnie.
Ronnie. So what is vector QP?
It's going to be x2 minus x1, y2 minus y1.
And then how do you find the magnitude of that vector?
You just square your xy is equal to, and then you take the square root of that.
Right. And what's the distance formula?
That. Okay.
Proved.
All right.
Yeah. Other questions? Yeah, Samuel.
Was there a bug on one of I forget what problem it was, but it was on the very bottom. It said yes or no. It was a yes or no answer, and I put in y and n, and I couldn't get it to be correct.
Does anyone know what problem that was? 3?
Yeah.
Number 1? Did it work for everyone else?
Was it like capital?
Yeah, maybe.
Yeah, I asked you.
It didn't work?
No, I did. If it were capitals, it worked.
Oh, sorry. They're saying you have to put capital Y or capital N. We can sit down and talk about it.
Capital, got it.
No, actually, it seems like it works both ways, so I don't know what happened with yours. But I'm happy to sit down and look at it with you. Technology, you know? All right, so you did the written homework. Did you do the written homework? So let's look at that. Let's talk about that. So we've talked about scalar multiplication, and that multiplies what times a what when you do scalar multiplication? I'll give you a hint. Scalar multiplication. Scalar times a vector, right? Scalar times a vector. That's scalar multiplication of vectors like 5, say negative 5v. That's one sort of multiplication of vectors. And what does this do to the vector v? Minus 5v. What does this do? Right. You all said. Makes it 5 times as long, but then turns it the other direction, right? Points in exactly the opposite direction. So that's scalar multiplication. It's like scaling, like magnifying and shrinking. And then we got to watch out for the negative, flips the direction. Okay? So this, now what you started working on was another kind of multiplication, which is called dot product. Dot product. So we got, you multiply the corresponding components, and then you add. So what, 25, 20, 15, 0. Is that right? Yeah. Negative 15, negative 20, negative 25. Okay. And so, what was that? That was like both that, and then like, is that right? And then like this, something like that. I don't know what, I'm just guessing. And then you're supposed to compare these down here, just to look at the ones that get the same answer. For instance, this one gives what? 25? Oh, thank you. Anyway, there's ones below, and the idea was you were comparing the answers and then looking at the vectors to make some kind of conclusions about something about what does this number have to do with the two vectors that where does this number come from? What's the meaning of the number? Okay? So what was one particular conclusion that you came up, specific conclusion that you came up with when you compared the numbers? Yeah, what's your name? Heather.
When they're perpendicular, it seems to be 0.
So when all the examples and when they were perpendicular, it was 0. Okay, good. Check. All right. What was another specific? So what we're going to do is we're going to make all these little observations and then try to put them all together to come up with one meaning for the dot product that fits all those little observations that we made. Nick, you got another one?
Any two vectors that were collinear or anti-parallel, their dot product was the maximum value.
Okay, so like this one.
Yeah.
If the vectors are the same, then he said we got the maximum value of the dot product. And what is that value relative to the two vectors? It's the magnitude of the vectors? Squared, or if you think about you got two different vectors, multiplied, right? So it was like the product of the magnitudes when they're in the same direction. Another observation. Yeah.
When the dot product was negative 25, it was a straight line.
Okay, so equal and opposite. So like if they're pointing in opposite directions, you got the opposite of what? The opposite of the magnitudes multiplied together. Yes, please.
The closer to 90 degrees, the smaller, the closer to 0, the absolute value of the dot product was.
Right. Okay, good. So looking at this progression here or along this way, what happens? As your angle increases and you get closer to 90, what happened to the dot product? Smaller and smaller until? Okay, so we want to think about, so this is coming, what is this number and what does it have to do with the direction, the relative direction of the two vectors? That's what it's really getting down to. What is this number a calculation of, and how does the direction affect that calculation? So that's, anyone? So now we're talking about maybe generalizing everything here together. Yeah?
It looks kind of to me like the cosine function, because when you have, for example, the first one is the most positive it can be. When it's 0, it's like cosine of theta when it's in the same direction, I guess.
Okay, cool. So it looks like it has the same relationship as cosine. That's good. And then what is the deal with cosine? What is it about cosine and the relative position of these two vectors getting this number? So like for 20 is 5 times what? Yeah, and where's the 4 coming from? The second vector? What about the second vector? Yeah, like it's like what? It's like the part of, it's how much of that is in parallel to the first one. And then how much of this is parallel to the first one? 3. And so the dot product is? And how much of this vector is parallel to this one? None. So do you see that it's a product? It's a product. It's a product of what two things? The magnitudes of the vectors, but only as much as the vectors are parallel, right? So it's like as much as the one vector is parallel to the other, it's that kind of part of the product of the magnitudes. So let's summarize here. I'm gonna go fast. You don't this is on video, so you don't need to try to copy this all down. Just think, and then if you want to copy it down later or take a picture of the screenshot of the video. So when they have the same direction, what was A dot B? If the vectors had the same direction? Product of the magnitudes. When they had the opposite direction? Opposite the product of the magnitudes. When they're orthogonal? 0. When A has a component in the same direction of B, that is, they're acute when they're tail to tail. So A has a component in the same direction as B. Positive, but less than or greater than the product of the magnitudes. Less than, right? Positive, but less than product of the magnitudes. And then similarly, if they're obtuse, you're negative, but less negative than the opposite of the product of the magnitudes. So putting all this together, that value of that dot product has a particular meaning. And we said, what? It's the product of the vector's magnitudes, but so in all these cases, we're multiplying the magnitudes together, but only, now the direction comes into it, only as much as they are in the same direction. So only as much as the one is in the direction of the other do you multiply that component of it to the magnitude of the other. So we're going to keep seeing, this is going to keep coming up throughout the course. We're going to see these different, we're going to come to a situation. It's like, okay, what do we apply? It's like, do we need the product in as much as they're in the same direction? And if that's the case, then we want the dot product. All right. Any questions on that? Yeah, please.
So the dot product doesn't have to be between negative 25 and 25. It was only that case because none of the components were more than 5 in the sheet, right? So if you have 6.
Yeah, so like, so if you had,
Yeah, it'd be 36 then.
so if you had a vector whose magnitude was, 7, and then you had another vector whose magnitude was, 11, then the maximum value of the dot product will be what? 77, okay? And then this one will be less than or greater than 77. Less than. So it will be only 7 times this much, right? This much of u. Whatever that much of u is, times 7 will be the dot product. Does that help? Yeah. Yeah.
The answers from a dot product, they scalar and vector quantities.
Well, what is the dot product? The dot product essentially is?
The product.
So what is that? Scalar or vector? Scalar, yeah. So when you do the dot product of two vectors, you get a scalar, which is the product of the magnitudes in as much as they're in the same direction, the vectors. All right, so let's talk about work. So now we're ready to do work in this class. We haven't done any work yet. Get it? I got jokes today. Work is defined as the total amount of force applied over distance. So we can investigate the amount of work to move an object, that's a scalar quantity, by observing the force applied and the displacement of the object. Those are both vectors, right? So, applied force is vector, and the displacement, where it starts and where it ends, that's also a vector. And then when you put those two together, you use the force to move the object, then there's a certain amount of work, which is a scalar quantity. Okay, so a girl pulls a wagon, force of 56 newtons, at an angle of 39 degrees above horizontal. So we got 56, the force is 56 newtons, how she's pulling. And for a distance of 8.1 meters. So there's the displacement vector. And so we want to figure out what's the work applied to the wagon by the girl. when she walks these 8.1 meters. So let's start by writing, can you write F and D in their component form? Can you write F and D? Hopefully, we can. So, key, take your pick. Can you write one of those F or D? Can you tell me what the components of either one of those is? Okay, tell me your name. Yeah. Tyler, take your pick. F or D in component form.
I don't know the calculator value, but it'd be 56 times the sine of 39.
Is that the X or the Y component?
That'd be the y.
Y component. So 56 sine 39. And what would be the X component?
So I'd say that.
You don't have to get your calculators out. This is perfectly good representation of those values for our purposes. Okay, did you get it right? Is that the components of F? Okay. And then D. Yeah.
8.1.
He wants 8.1 and 0. Yeah, it's all in the X direction. It's all, so 8.1 comma 0. Okay, so we got those. Is that, can you read that in the back? Okay. All right, so what component of F, one, the X or the Y or both, contributes to the work done? Does the X component or the Y component or both contribute to the work? So what is the Y component? Does the Y component helping her move the wagon across the ground? No, it would be like trying to lift it up, right? It would have nothing to do with, so it's just the X component that is resulting in the wagon moving. So only the horizontal component, okay? So to calculate the work done, what? It's force times distance. So the force we care about is what? How much force? 56 cosine 39, right? 56 cosine 39, and the distance is 8.1. So we can do this without vectors, right? So once I have those components of those vectors, now I can just apply the basic formula for work, which is just force times distance, regardless of vectors, and it's 352.5 joules. Make sense? So we only need that X component, and then we're going to just multiply it by the distance. All right, so notice the work is the product of the magnitude of the force and the distance in as much as they're in the same direction. You notice that? It's like we only want the part of the force that's in the direction of D. And it was like the product of the magnitudes in that way. So, should sound familiar. What is this? This is just feel a lot like our previous discussion of the dot product, right? So this is dot product. So, and this is where cosine comes in, right? F cosine theta times the magnitude of D. Here's another way to calculate the dot product, is the product of the magnitudes times the cosine of the angle between them. So you guys in your exercises, in the homework, it was multiply the components and add. But now we got the meaning of it. The meaning of it is what? The product of the magnitudes, F times D, in as much as they're in the same direction. And like someone said, cosine theta. So let's do it the way that you guys did it for your homework. So what would you get if you just did the product of the components added together? What would happen?
Y component hands on to 0.
It's the same thing, right? So if you do the X component times the X component plus the Y component times the Y component, or the original way that we learned dot product, you're going to get the same thing. Does So that says, right on the black line, it says in big bold letters, remember, there are two ways to compute the dot product. That's what it says. To remember, and they give you the same value, so use whatever's most convenient. So this says, remember. Two ways of computing the exact same number. Sorry. That says dot product. So remember, there are two ways to compute the dot product. So if you need something that the dot product computes, you can do it by multiplying the corresponding components and adding. But this is another way now. So the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between them when they're tail to tail gives you the same value. And that actually reflects the meaning that we were working on better, right? That's really reflective of the second way of this meaning, the product of the magnitudes in as much as they're in the same direction. Questions on the work example? Okay, let's try another one. So, how much work is done to push a box from the point -2, 1, 0? So let's find that point. -2, 1, 0 is about here. I want to push the box up the ramp to the point P if the force applied is 8, -15, 0. And so it's 8, -15, 0. Let's see. 8. How does that push it up the ramp? Oh, right. 8, -15. So I'm kind of pushing like this. And my displacement vector would be like this. So I'm going to need to find the angle between those two vectors, right? That doesn't sound so fun, does it? Do I need to find the angle between those two vectors? Why not? Right, so, the work is going to be, yes, the work is going to be f d cosine of whatever angles between those R3 vectors. But, have fun finding that angle, right? So instead, we can do what? I mean, this is the dot product. But it's not the way we want to find the dot product, right? How do we want to find it? Okay, we want to do, we'll do d dot f this way. So what is the displacement vector? -1, -7, 2, dot 8, -15, 0. Which will accomplish get the exact same value as this, right? So we get -8. What's that? 105. -97 or +97. Did I give you? And that would be foot-pounds. Foot-pounds is English units for work. Pounds times feet, foot-pounds. Okay, what if I do want to find that angle? So now we have a way of finding the angle between these two vectors. So if I put them tail to tail, here, I put the force vector, whatever it is, like this. So there's F and D. And so question is, what is that angle? How can I find that angle now? So now this is kind of not, it doesn't have to be a work problem anymore. I've got two vectors. I know what they are, and I want to know what the angle between them is if I put them tail to tail. So how can I do it? Yeah.
I think you would divide 97 by the magnitudes of f and d,
Okay.
and then take the arc cosine of that.
Yeah, because right. So this is one way to compute the dot product. This is the other way. They're equal, and we know it's the dot product is equal to 97. So this thing is equal to 97. So I can solve for the angle this way. So the dot product provides a way of figuring out the angle between two vectors when they're tail to tail. As long as you have the components, you can compute the dot product the easy way. You can find each magnitude, divide, and do arc cosine. So it would be 97 divided by magnitude of F is and magnitude of D is and that'll be cosine theta, and it'll be the arc cosine of that whole thing. So, right? To get theta, it'll be the arc cosine of that. Make sure you know if you're in degrees or radians on your calculator. Does someone punch it out so we can get the number? Did you get something?
I have the value for the vector magnitude of f, which is 17, so I'm just working it out. 97 over 17.
It's going to be an acute angle, maybe 20, 30, 40 degrees, something like that, I'm guessing. As soon as you get an answer, shout it out. We'll get confirmation. We'll move on.
9.1.
What'd you get?
39.1.
39.1. Really? That's the same angle as the previous.
That's right. You should just take the arc cosine.
39.1?
Yeah.
Was that the angle in the previous problem? 30. Yeah, that's crazy. That's total coincidence. There's absolutely no connection between these two problems. Okay, understand how to use the dot product to find the angle between vectors. Does it make sense? Any questions on what I did there? Okay, so there's another thing related to dot product. It's called projections. Projections. The first is the scalar projection, and then there's the vector projection. So we're going to be looking at the scalar projection of B onto A and the vector projection of B onto A. So the scalar projection is, it's the magnitude of the length of how much when B projects onto A. So it's like if you were shining a light down perpendicular to the A vector, it'd be like the shadow of B on A, and it'd be the length of that. Does that make sense? So this length right here it's basically how much of B is in the direction of A, right? As a scalar. What length is the projection of B onto A? Okay, so you know that from before calculus. So how could I want to calculate that length. What is that length? That length that I wrote would be what? Magnitude of B times. It's only part of the magnitude of B. What part is it? Cosine, right? The adjacent, right? So it's the adjacent part. So that's what that is. The scalar projection is magnitude of B cosine theta. But that looks a lot like what? The dot product is what? What's the dot product of A and B? Magnitude of A, magnitude of B, cos theta, right? So this right here is the scalar projection of B onto A. So we can rewrite that. How can we isolate magnitude of B cosine theta equals? Therefore? See that? So if I just isolate that part of it right there, that's the scalar projection. It would be dividing both sides by the magnitude of A. So it is. What's convenient about that versus this way of doing it? So what is this? How is this helpful to find that scalar projection versus that? You don't need the angle, right? So this is a way of getting that value, how much of B projects onto A, without knowing the angle. Because we could calculate A dot B the other way, right? We could calculate A dot B with the adding up the products of the components. Okay? So that's the scalar projection of A onto B, B onto A, excuse me, B onto A. And so then what about the vector projection? Does it show up as orange? Yeah. So the orange vector. So now you've got all the tools to write that vector. So can you write that vector, which is the vector projection of B onto A? Can you do it? Can you use previous things we've learned, put them together to do that? Can you write that vector? Yeah, so it's okay. All right, hold on a sec. Hold on a sec, everyone. Vector projection. Yeah, so what was your thinking about this? Yeah. Okay.
And then for the y component, it would just be the same as A because it's like on top of it.
Okay. So you did put this for the x component and then the y component of A, like that? Okay, so that's a good idea. How does this vector relate to A? How does that vector relate to A? Yeah, Dylan.
It's in the same direction.
Uh-huh. It's in the same direction. So how do we get a vector in the same direction? Christopher?
We take like a unit vector.
Okay.
And then we multiply by the new prime magnitude.
Okay, good. So we want to. So it's like turn A into a unit vector and then scale it to the length we want. We saw that last time, right? So Christopher, tell me, how do I? So what am I gonna do?
So if we had A, like
Uh-huh.
vector A,
Uh huh.
times the magnitude of vector B all over the magnitude of vector A. So A, that over the magnitude of vector A.
Okay. So what is this first of all?
That would be the unit vector in the direction.
Unit vector in the direction of A, and then.
And then times the magnitude of vector B. Or wait.
So what? How much do we want to scale it by? How much do we? What's that?
So it'd be the x component would be, yeah, yeah.
What would it be?
B cosine theta. Or the magnitude of B cosine.
Okay, which is the same as?
The length.
Which is this, right? Let's use what we found, right? We're going to use what we found. Yeah, so we want to scale it by magnitude of B cosine theta, but we're going to scale it using this version of it, right? So we're scaling the unit vector in the direction of A by the amount of the scalar projection. All right, so we can actually combine these. We can pull this magnitude out. So for the scalar, we can do A dot B over the magnitude of A squared That's our scalar on A. And that gets us that orange vector there. That's the vector projection. Again, found with not having to know the angle. Okay, so this is, what does it say? The vector, the scalar projection, they use components, COMP. And then it's of B, so B is big up here, onto A is little subscript A. That means the scalar projection of B onto A. It's a scalar, it's just a value. And then the vector projection, they use again, of B onto A. It's a little subscript down there. All right, in the easiest way that you can, I want you to express that vector in the easiest way possible, with the least amount of work. I want you to express the blue vector right there. Think about it. How could you express the blue vector, which is kind of like what? It's like the perpendicular projection onto A. It's the part of B that's perpendicular to A when projected onto A. So what would be the easiest thing to write down that would get you that vector? Think about it. Okay, let's see. Any ideas? Tell me, what's your name again? Emily. B minus A?
Oh wait, sorry, no, B minus the projection.
She wants B minus the orange vector. Is it minus the orange vector? You see that? Yeah, because this is what? This is the other component of B. So B could be written in horizontal and vertical components and would look something like this. Try it again. So B can be written in horizontal and vertical components with an I and a J, kind of like what I did in the green there. But it can also be written in components relative to A. That's what we're doing. So we're writing the parallel component to A. That was the projection, vector projection. And then there'd be the other component to complete B, right? Which would be the other perpendicular to that. So that blue vector, I'll write it in blue. The blue vector is, I'll call it just V for vector. Would be what? It would be what you would need to add to the vector projection to get B, right? Those two added together, orange plus blue, would give us the vector B. So V therefore is B minus the projection of B onto A. Do you see it? So this vector projection, it's a way of finding an alternate set of components that make up B in the parallel to another vector, rather than the I and J version, like the horizontal and vertical. You can find components of B in any direction specified by A. And so then the parallel to A is the vector projection, and then perpendicular to A is the difference of your starting vector and that vector projection. Does it make sense? It should make sense. Yeah?
So is the scalar projection just the magnitude of the vector projection?
Yes, exactly. So the magnitude of this vector is that, right? Because we took because we took this unit vector and scaled it by that much. Other questions? Okay, so let's just in the last minute here, let's just practice. We'll just draw a few. So draw any two on your paper. Draw any two vectors, any direction, any magnitude, tail to tail. So just everyone will have something different. So just be creative, right? Down and to the left, a little bit up and to the right, something like that, right? And then any lengths you want, so you'll have 2. So I'll throw one up here. Like this, a super long one like this. Okay, there's mine. So you might have something. You're gonna have something different. So call one B and call the other A. Call one B and the other A. And now I want you to sketch the vector projection of A onto B. Can you sketch, for yours, sketch the vector projection of A onto B? Okay, so I'll do it for my example, and then you can see if yours is right. So when you say A onto B, it's the vector projection of A onto the line through B. So if you need to extend B into a line, you might have to do that. That's what I have to do. You might have to start by extending the vector that you're projecting onto into a line. So I did that with a dotted line. And now my vector projection of A onto B, let's go with orange, and orange seems to be the color. And I can make it thicker. It's so cool, right? So that would be my vector projection of A onto B. All right, so you can just take the last minute to check what you did with the person next to you. See if you guys agree with, so get a pair up and see if you agree with the pictures that both of you drew. Go.
I mean, I want to draw these down.
Yeah, that's why I flipped to a whole new page.
Okay, so in the homework, I can ask you a question. In the homework, you have to, I didn't do any examples using it. You have to be on the lookout. This is now in your toolbox. It's a really helpful tool if you can see the situation and apply it, okay? So be on the lookout for chances to use. There are problems in the homework where using these scalar vector projection is going to be the most efficient way to get it done. But you have to recognize that in the given situation. All right, so, and then I'll post the first written homework. Will be due Wednesday at midnight. And then the next, you got a web work due today at 5, and then the next one, the new stuff will be Wednesday at 5. Have a great long weekend.